we are going to discuss the displacement analysis of planar robots. So, to give you the overview of today's lecture, we are going to look at the forward and inverse kinematics problem with an example of an RP open chain planar manipulator. So, just to reiterate our plan for robot displacement analysis, we are going to discuss planar robots first, open chain configurations, and then planar robots with closed chain configurations. So, in today's lecture, we are going to look at an example of an open chain planar robot. So, here we look at the problem of displacement analysis, which we have defined before. So, there are two problems: forward kinematics, in which the actuator inputs are given and we have to find out the output link displacement. So, in the case of a robot manipulator, it would be the end effector displacement and orientation. The inverse kinematics problem, in that we have a specified output, that means our end effector displacement, the position and orientation of the end effector, these are specified. We would like to find out what should be the actuator input. So, the inputs are the actuator displacements and the outputs are the end effector position and orientation. So, we have looked at 2 degree of freedom kinematic chains with a 2R manipulator example. In today's lecture, we are going to look at an RP manipulator, which also has 2 degree of freedom, and subsequently we are going to look at 3 degree of freedom kinematic chains. So, this is a schematic representation of an RP manipulator. So, here is the forward kinematics problem. So, given the inputs, so input angle theta, so this is the input angle theta, and the throw of the prismatic actuator. So, the throw of the prismatic actuator I am measuring so this is S. So, that is the throw of the prismatic actuator. So, this is a P pair and here we have a revolute pair. So, the forward kinematics problem is, given this theta and S, we have to find out the location of the end effector. So, given theta and S, we have to find out the location of the end effector. So, here is the end effector location, this point. Phi is the angle of orientation of the end effector, as you can see. This angle alpha is a fixed angle. It seems to be 90 degree, but it can be a general angle alpha. So, I can have this angle is alpha. This is a fixed angle. So, here we have the forward kinematics problem. So, let us look at how to relate the end effector positions x c and y e to the input variables theta and s. So, here I have the schematic of the RP manipulator once again. I have to relate the location of this end effector point in terms of theta and s. So, this is x e. So, what is x e? X e is summation of these two distances, this plus this. Now, this distance you can very easily write as L 1 cosine theta, where cosine I am writing as C. C stands for cosine. So, L 1 cosine theta. Now, this distance I have to relate with S. Now, you can see that this angle is alpha. So, this angle is alpha. So, if I take a horizontal line, then this angle is theta, because this dashed line is oriented with L 1, the first link, and this is the horizontal which is parallel to the x axis. So, this angle is theta. So, therefore, this angle so if I have to relate this angle, then I can write that this is theta being measured, all angles being measured positive in the counterclockwise sense. So, theta minus alpha. So, theta minus alpha. Because all angles are being measured positive in the counterclockwise sense. Angles are measured positive in the counterclockwise sense. So, this angle is actually a negative angle. So, therefore, I can write x e equal to L 1 cosine theta, and plus this distance would be S cosine theta minus alpha. So, this becomes plus S cosine theta minus alpha. So, that is the x location of the end effector. Y location of the end effector so this distance is L1 sin theta. L1 sin theta, and we have to add to that this distance. Now, that is in the negative sense. So, therefore, you can see that y e is L1 sin theta plus S times sin theta minus alpha. Now, because theta minus alpha is a negative angle, so that takes care of this subtraction. So, I have related theta and S to x e and y e. So, to reiterate, this theta minus alpha is a negative angle because it is here, it goes in the clockwise sense. So, that is negative. So, that takes care of the sign of this distance that we have added to L1 sin theta. So, just to write it out formally now. So, end effector position coordinates x e is L1 cosine theta plus S cos theta minus alpha, and the y position is L1 sin theta plus S times sin theta minus alpha. Now, this theta minus alpha, remember, is this angle. So, this is theta minus alpha, and alpha is this whole angle. And you can also relate, you can also check that this phi is nothing but this theta minus alpha. So, therefore, this phi is equal to theta minus alpha, which is the orientation of the end effector. So, to present that formally, so the end effector orientation coordinate phi is given by theta minus alpha. So, we are measuring angles counterclockwise. Any angle being measured in the clockwise sense will be negative. So, we have looked at the forward kinematics problems. We have found out the position coordinate x e and y e, and we have also found the orientation coordinate phi in terms of theta and s. Now, the inverse kinematics problem. So, here we are given x e and y e, which are the coordinates of the end effector. So, this point coordinates, and we have to find out the angles theta, we have to find out this angle theta and the throw of the actuator. So, this angle once again is alpha. So, measured in the negative sense. So, that is the inverse kinematics problem. So, let us proceed with that. We will start off with the forward kinematics relations. So, these are the forward kinematics relations. So, x e and y e in terms of theta and s. So, remember we are given x e and y e, we have to find out theta and s. So, if I do this step, so x e minus L 1 cos theta 1. So, I get this term on this side, this term on this side, and take the ratio, then I can eliminate s. I can eliminate s. So, I have this ratio. I have opened up cosine theta minus alpha and sin theta minus alpha, as you see here. Now, I am going to take this, simplify this expression as follows. So, I can write x e sin theta cos alpha minus x e cos theta sin alpha minus L 1 cos theta sin theta cosine alpha plus L 1 cosine square theta sin alpha, and that must be equal to y e cosine theta cosine alpha plus y e sin theta sin alpha minus L 1 sin theta cosine alpha minus L 1 sin square theta sin alpha. So, we know x e y e, we have to find out theta from this equation, because s has already been eliminated. So, let us rewrite this equation in this form. So, I will first collect all the coefficients of sin theta. So, y e sin alpha here you will find these two terms. So, here we have L1 cosine theta sin theta cosine alpha, here also on the other side also we have L1 sin theta cosine alpha with the same sign. So, this cancels off and these two terms can be combined. So, let us proceed then. So, here I had this is the first expression minus x e, I will take this term so that is the coefficient of sin theta. Now, cosine theta plus y e cosine alpha plus x e sin alpha into cosine theta, and that must be equal to, I will take this term on the left hand side. So, I have L1 sin alpha. So, that completes the simplification. So, we have this new equation which can now be written as A sin theta plus B cosine theta is equal to C with the appropriate definitions. So, this is A, this bracketed quantity is B and that is C. So, let me now represent this formally. So, A sin theta plus B cosine theta is equal to C as we have obtained, and these are the definitions of A, B and C. So, here we have an equation in which A, B and C are completely known because y e x e are known completely and alpha is a fixed angle. So, A and B are completely known and C is also known. So, I have theta as the only unknown which I can solve. So, let us go through the solution of this equation once again. Before we go through this solution of this equation, let us look at the solution for S. So, that remains. So, we have an equation from where to solve for theta. We also need S. So, how to find out S? So, once again look at our master equations, which are the forward kinematics equations. So, in this you will find if I multiply the first equation by sin theta, the second equation by cosine theta and subtract. So, first equation by sin theta, second equation by cosine theta, and I subtract. Then on the right hand side, the first terms cancel off, and what I am left with is s cosine of theta minus alpha sin theta minus sin theta minus alpha cosine theta. Now, this right hand side therefore becomes s times, so sin theta cosine theta minus alpha minus cosine theta sin theta minus alpha is sin of theta minus alpha. So, it is sin of alpha. So, therefore, s will be equal to x e sin theta minus y e cosine theta whole divided by sin of alpha. So, this I am going to now show you formally. So, this is what I have done. So, therefore, s is x e sin theta minus y e cosine theta whole divided by sin of alpha. So, once I have solved theta from this equation, I can substitute in the equation for s and solve for s. So, for every value of theta that I obtain, I will obtain a value of s. So, we are left with the solution of this equation, a sin theta plus b cosine theta is equal to c. So, that is what we are going to look at next. So, once again, as we have discussed, so we make a substitution, we define a variable x as tan theta by 2 and we represent sin theta in terms of x and cosine theta in terms of x and substitute in our master equation and obtain this quadratic equation, from where we find the roots. So, the solutions of x and hence the solution of tan theta by 2. So, in terms of a, b and c, we have these solutions where a, b and c we have defined earlier. So, when I have these solutions of x, I can solve for theta. So, let us look at that. Here the complete solution has been written out for you. So, from the previous equation, so from here I have obtained these two solutions, theta 1 and theta 2. Theta 1 and theta 2, these are the two solutions of theta which correspond to this difference in this sign, and s is then calculated using this expression. And as we have noted before, that when we want to get the quadrant correct in a computer calculation, then we must use this A tan 2 function. So, then you will get this theta 1 and theta 2 in the proper quadrants. So, you need to give the numerator and denominator separately. So, for example, in this solution this is y and this part is x. So, you have to give A tan 2 this y comma x, then you will get theta 1 in the correct quadrant. So, this completes the inverse kinematic solution. Let us try to understand this solution graphically. So, I have written out the solution on the left. Now, what do we have to do? We are given, remember we are given x e and y e. So, this point is given to us. So, this is x e, this is y e. So, this the coordinates of this point they are specified. Now, depending on this angle alpha, if this angle alpha is 90 degree like it appears here, so I have to drop tangents because this prismatic pair maintains this angle of 90 degree. Suppose alpha is 90 degree, then I have to drop tangents to this circle whose radius is L1. Radius of this circle is L1. If alpha is 90 degree, then I have to drop tangents. Now, you can drop two tangents. This is one tangent in black and this is another tangent. So, therefore, I can have another configuration like this. This is the prismatic pair. So, this is the other configuration. So, these are the two solutions. So, you have two solutions of theta. And correspondingly you will get two values of S. Now, these two values of S, if you think a little bit, they will just differ in sign, because if this black configuration has to come to this blue configuration, then it has to rotate all the way like this and the end effector has to come out from this side. So, that will give a negative value for S. So, this is positive S and this side would be negative S. So, this is negative S. So, this is the geometric interpretation when alpha is 90 degree. If alpha is an arbitrary angle like this. So, this angle remember is alpha. So, therefore, this angle is also alpha. If this link length is L1, then this radius of the circle should be L1 sin alpha. So, this distance, perpendicular distance from the direction of the prismatic pair. So, this angle is 90 degree. So, this radius of this circle is L1 sin alpha. Now, given this point, we need to drop tangents to this circle. So, this is one tangent. I can drop another tangent. Like this. So, the other configuration this is the other configuration of the manipulator. So, again you have two values of the angle and hence two values of S correspondingly. So, that is the graphical interpretation of the solutions. Now, the workspace, as you know that this prismatic pair it translates like this. So, therefore, this end effector can move on this line. Suppose this is the maximum throw of the prismatic pair, then this is the maximum reach and rotation of this angle will generate the workspace. So, suppose this is the minimum and this is the maximum throw of the prismatic pair. Therefore, I generate this annular region, a thin annular region as the workspace of this manipulator. Now, depending on joint limits, this workspace can change. This is the ideal situation when there is no limit on the revolute pair, but obviously from physical construction point of view, there will be limits on these joint angles. So, the workspace will be smaller than this and you can find out the workspace. So, to summarize, we have studied the displacement analysis with the example of an RP open chain planar manipulator. We have looked at the forward and inverse kinematics problem and looked at also the graphical interpretation of the solutions and the workspace of the manipulator. So, with that I will close this lecture.